Hydrostatic pressure and fluid force. Let's take some time to try to understand hydrostatic pressure. If you have ever gone swimming, you know that the deeper you go underwater, the more pressure you feel. Do you ever wonder why? As you go deeper and deeper underwater, you have a taller and taller column of water above you, pushing down on you. If we place a thin plate of area A horizontally underwater at a depth D, then the volume of that column of water above it would be found by calculating volume is equal to the area of the thin plate times the depth, or V equals A times D. Now, before we examine hydrostatic pressure, let's review the concept of density. Density measures how tightly matter is packed together. So here are some examples of liquid density. The more dense the liquid is on the bottom. So honey has matter more tightly packed together than does liquid hand soap, then water, olive oil, and then ethyl alcohol. So liquids have different densities as shown here. So to calculate hydrostatic pressure, we will need to consider the density of the liquid. Let's finally examine the formula for hydrostatic pressure. Hydrostatic pressure is equal to the force that's exerted by the liquid divided by the area that the force is being applied to. Well, the force exerted by the liquid is equal to the weight density of the liquid times the volume of the liquid, how much there is. And that's still divided by area. Well, we said that the volume of that column of water was equal to the area times the depth. So volume is equal to area times depth. Well, notice that area over area is just 1, and so it cancels and leaves us with the idea that hydrostatic pressure is equal to the weight density of the liquid times the depth. Let's formalize hydrostatic pressure. The pressure of a fluid standing still is found by using the following formula. Pressure is equal to the weight density of the liquid times the depth, or P equals W times D. If we're in metric, then we're going to break down the weight density as the mass density, rho, times gravity, and then times depth. So for units in the imperial system, P is pressure in pounds per foot squared, W is the fluid's weight density in pounds per foot cubed, and D is depth in feet. In the metric system, P is pressure in newtons per meter squared, rho is the fluid's mass density in kilograms per meters cubed, G is gravity, which is in meters per second squared, and D is depth in meters. For the weight density of water, and we'll often have our fluid be water, we'll use the weight density W to equal 62.5 pounds per foot cubed, or the mass density is 1,000 kilograms per meters cubed. And again, in metric, we'll need to multiply rho, the mass density, by gravity, 9.8 meters per second squared. Now we can finally start talking about fluid force, and we'll start with fluid force on a constant depth surface. So the total fluid force on a constant depth surface is found by using fluid force is equal to pressure times the area of the surface. So the force exerted is equal to the pressure times the area of the surface that pressure is being applied to. So we have F is equal to P times A. Well, we just said that pressure was equal to the weight density times the depth. So fluid force is the weight density times the depth times the area of the surface. Or in metric, weight density is still. Now we can finally talk about fluid force on a constant depth surface. The total fluid force on a constant depth surface is found by using the following formula. Fluid force is equal to pressure times the area of the surface. So here, the bottom of this pool is at a constant depth. Every single point on the bottom of this pool is at a constant depth. So to measure the fluid force on the bottom of the pool, we would multiply pressure times area, P times A. Well, pressure, we just said, was the weight density times the depth. So weight density times depth times area, or in metric, mass density times gravity times depth times area. Let's look at our first example. Find the total fluid force at the bottom of a 15-foot by 20-foot rectangular freshwater swimming pool 4 feet deep. So here is basically a rectangular prism representing a pool, and we want to find the fluid force at the bottom of the pool. So this is a constant depth surface. And the dimensions of this pool are that the bottom is 15 feet by 20 feet. So we'll say this is 20 feet by 15 feet with a depth of 4 feet. Now the formula for fluid force, and this is going to be in imperial units, we're going to have the weight density times the depth times the area of the surface. The weight density of the liquid is the weight density of water, because this is a freshwater swimming pool. And weight density of water, we said we were going to use 62.5 with the units of pounds per foot cubed times the depth, and the depth of this pool is 4 feet, times the area of the surface, that constant depth surface. So the area of this rectangle at the bottom is 20 feet times 15 feet. So this part is 20 feet times 15 feet. So let's see what's going to happen to the units here first, and then we'll multiply all of the numerical values. So on the denominator here, I have feet cubed, and notice if I multiply all of these together, I'm going to have feet times feet times feet, which is feet cubed. So the units that are going to cancel is feet cubed, and all that's going to be left is pounds, which is a unit of force. And so now we multiply all of the numerical values, 62.5, 4, 20, and 15, to arrive at 75,000. So the fluid force is 75,000 pounds. We didn't do any calculus in that last example, so let's extend this concept to calculus. We can use this concept of a thin, flat plate to represent a surface like the side of a swimming pool, or let's say the side of a submarine. If a plate is submerged horizontally, like in our previous example, so if we think about the bottom of the pool as a plate that's submerged horizontally, every single point on that plate was at a constant depth, and we can use that formula for fluid force, F equals weight density times depth times area, to calculate the total force. But if that plate is submerged vertically, so let's imagine now that we don't want to calculate the fluid force on the bottom of the pool, but let's say what's the fluid force on one of the sides of the pool. So this is not at a constant depth. There's different amounts of pressure that are being applied at the bottom of this plate than at the top of the plate. So the depth is not constant anymore, since it varies from the bottom to the top of the plate. Now let's extend the idea to calculus to find the total fluid force on a varying depth surface. We integrate to add up the forces on the infinite levels of depth from bottom to top of the plate. So to calculate the fluid force, we're going to find the integral from A to B. So those are y values. Note that the plate runs from y equals A to y equals B. And to calculate the force, we're still going to need the weight density of the liquid times the strip depth. So the strip depth is a function of y. So as I go from A to B, the depth of each strip is going to be different from the surface of the water. So the first strip depth will be the biggest. So as I start down here at A, I'm furthest from the surface of the water. And then as I move all the way to B, my strip depth is going to get closer. So here's one sample strip here at some Y value. So we can see the strip depth is that vertical distance to the surface of the water. And so that's going to be a function of Y. And then we have times the length. L of Y is the horizontal length of the strip, which can also vary from bottom to top. So on this shape, we can see that the strip length is going to increase until it gets to right about the middle there. And then the strip length is going to get shorter again. So we're going to potentially have two functions of Y in the integrand of my fluid force integral. In this example, we want to set up the integral needed to find the fluid force on one side of a 4 foot by 4 foot square plate if the plate is at the bottom of a pool filled with water to a depth of 6 feet and resting vertically on a 4 foot edge. So let's construct a diagram. First, I'm going to construct the plate. So the plate is a square plate that is submerged vertically. So I'm going to draw a 4 foot square. And we're saying that this square is submerged vertically in a pool, and the depth of the pool is 6 feet, and the bottom of the plate is resting on the bottom of the pool. So that means that the surface of the water is 6 feet above the bottom of the plate. So here is my pool. So we're imagining this square plate that's like standing up on its side in a pool, and we're thinking about the pressure that's being exerted on every level of this plate, and it's on the bottom of the plate is touching the bottom of the pool. Okay, so now we want to start to build our integral. Our fluid force is going to be the integral from y equals a to y equals b. So what are our y values going to be? Well, what we're going to need to do in all of these problems is establish where is our x and y axis, and really where is our origin. And we have the choice to kind of put it wherever we want. So I'm going to choose to put my x-axis along the bottom of the pool here. So here's my x-axis along the bottom of the pool. Kind of missed a little bit. Sorry about that. And then I'm going to put my y-axis. Actually, I'm going to just cut straight through the square. And I'm going to put my y-axis like right in the middle of the square, going straight up and down. So that's my y-axis. All right, so now that I have an x-axis and a y-axis, the limits of integration, where does this shape extend from on the y-axis? Well, from 0 as a y value all the way up to 4. So we're calculating the force on the shape, which extends from y value 0 to y value 4. So this is y equals 0 here to y equals 4. So my integral so far for fluid force is the integral from y equals 0 to y equals 4. We need the weight density of the liquid. So the liquid is water. I'm in a swimming pool filled with water, and we are in the imperial system because we see feet involved. So we're going to use that 62.5 pounds per foot cubed. So that's the weight density. And then we need times the strip depth. So the strip depth is going to be a function of y. So the depth of each strip is going to vary as I extend from y equals 0 to y equals 4. So let's kind of think about the first strip. So the very, very first strip down here along the bottom of the square is at a depth of 6 feet from the surface of the water. So when we talk about strip depth, it's from the surface of the water. So that first depth is 6. And now let's just say I move up to y equals 1. So if I'm at y equals 1, then what is the strip depth now? Well, it's going to be the surface of the water, 6 feet high, minus 1. So it's going to be 5 feet deep. So a function to represent the strip depth at any y value between 0 and 4 is going to be represented by the quantity 6 minus y. So we want to be able to pick any generic y value between 0 and 4, and if I plug it in to 6 minus y, that will tell me the depth of that particular strip. So 6 minus y is the strip depth function. And then last but not least, I need to find the length of each strip. And thankfully in this example, the length of each strip is not actually a function of y, it happens to be a constant. So for any y, any generic y I choose between 0 and 4, how long is that strip going to be? Well, this is a square, and so each one is going to be a length of 4 feet. So our strip depth was 6 minus y feet, so that's how deep I was, and then our strip length is going to be just 4 feet. It's going to be a constant on this example, dy. So this is the setup of the integral. I am going to do just a little bit of cleaning things up here. So I can multiply the 4 and the 62.5. That's going to be 250. That's a coefficient that I can go ahead and pull to the front of the integral. So I have 250, the integral from 0 to 4, and then I have 6 minus y as my integrand, right, dy. Now let's look at the units real quick and see what units are left over in the integrand. So we have pounds per foot cubed times feet times feet. So only 2 of the feet on the bottom here, since this is feet cubed, only 2 are going to cancel out. In our next example, we have a flat isosceles right triangular plate with a base of 6 feet and a height of 3 feet is submerged vertically, base up, 2 feet below the surface of a swimming pool. All right, set up the integral needed to find the force exerted by water against one side of the plate. All right, so let's go back to the first sentence. An isosceles right triangular plate. So an isosceles right triangle, the base of the triangle is 6 feet, the height of the triangle is 3 feet, and it's submerged vertically base up. Base up. Okay, so the base, we're told, is 6 feet. So I'm going to sketch myself isosceles triangle with a base of 6 feet face up, or base up. So here 6 feet is on the top, and then this is isosceles, meaning that the other 2 sides are the same length. Do my best to try to make them look the same. And then the height is 3 feet. So right here, the height is 3 feet. So this shape is submerged 2 feet below the surface of a swimming pool. So here, this little distance is 2 feet, and that's under the water. So this is a diagram of the situation. A right triangular plate, that's isosceles. So again, these are supposed to be the same side length here. It doesn't quite look like it, but it is. And the base is 6 feet, it's base up, so that's on the top, and its height is 3 feet, and the top is 2 feet below the surface of the swimming pool. All right, so let's go ahead and start to set up our integral. Well, in order to do this, we need to establish where the origin of our xy axis is going to be. And on this problem, I'm going to go ahead and let, I'm going to let the origin be right at the very bottom of the triangular plate. So that's going to be my origin. So I'm going to draw my x-axis. I'm going to move it up a little bit. My x-axis right here, my y-axis straight up. I'm going to move it a little bit. All right. So there's my x and my y-axis. And let's go ahead now and start to build the setup of the integral. So fluid force extends from wherever the plate exists, right? Whatever I'm actually exerting force on. So the y values here are going to extend from y equals 0 to y equals 3. So we have y equals 0 to y equals 3. The fluid force, once again, or excuse me, the weight density of the fluid, W, because it's water, is 62.5 again. This time I'm not going to include units at each level, we'll just include units at the end. So 62.5 times the strip depth. So remember, the strip depth is going to be a function of y. So if we just kind of pick some generic y value between 0 and 3, we need a function that's going to represent the depth at y. So from the surface of the water down to that y value. Okay, so the surface of the water, because of where we put our origin, the surface of the water is at a y value of 5. So here we have this height of the triangle is 3, but then it was 2 feet underwater. So up here, way up here, the surface of the water is at y equals 5. So to find the strip depth, what we really need to do is create the function, the height of the water minus y. So the height of the water is 5 in this case. So we're going to have 5 minus y in parentheses as a quantity. So this will give us the height of any strip between 0 and 3 that is created. And then finally, I have to write the strip length as a function of y, because on this example, each strip is not going to have a constant length. It is going to vary as I move from y equals 0 to y equals 3. So if I kind of sketch a sample strip right here, let's say, this is shorter than, let's say, if I put another sample strip up here, that's going to be a longer length as I move from 0 to 3. So I have to figure out how to express this length as a function of y. And to find that length, to find L of y, so this is going to be L of y, I'm going to need to find the right function minus the left function. So I'm going to need to figure out what is the equation of the right side of this triangle and what's the equation of the left side of this triangle, so I can find this length, L of y. All right, so how do I find the equation of this line right here? Well, if this is the origin, this is a linear function. A line is of the form y equals mx plus b, and my b value in this case is 0 because the y-intercept is 0. So what I really just need on this one is the slope. And here I can actually find the slope by noticing how I would go up 3 units. So if I think about calculating from point to point to find the slope, I have to go up 3 feet. And if this base is 6 feet, then half of it would be 3 feet. So I'm going up 3, right 3. So my slope is 3 over 3, which is just 1. So my slope is 3 over 3, or just y equals 1x. All right, but I want L to be a function of y, so I don't really want to think about this as y equals x. I kind of want to think about it as a function of y. I want to think about it as x equals y. So this right side equation is x equals y, and so I need to do right minus left. So what's the other side here? Well, the other side is simply just going to be y equals negative x, because I'm going to go up 3, left 3 if I'm going from point to point. So still a y-intercept of 0, but then up 3, left 3. So this is y equals negative x, or x is equal to negative y. So now L of y, we can solve this off to the side if it's helpful. So L of y is going to be right minus left. So the right function as a function of y is just y. So y minus negative y. So we're doing the right side minus the left side. So y minus negative y, that's y plus y. That's 2 copies of y. And I mean, that should make sense as well. So this, the right side, the distance here is y, and we're just doubling it because of symmetry. So the function for the length at any y value is 2 times y. That's what we're going to substitute in over here. 2 times y dy. And so on this one, we can multiply the 62.5 times 2y, which is 125y. I can pull the 125, the coefficient part, to the front. So 125, the integral from 0 to 3 of y times 5 minus y dy. And so the overall units of the final answer will be in pounds. So the units here are going to be in pounds per foot, but we're integrating over feet, so we'll have a final answer here of pounds. In this next example, we have a vertical plate is submerged in water as shown. Find the exact hydrostatic force against one side of the plate. So our diagram shows a circular vertical plate with a diameter of 4 feet that is submerged underwater. So the very top of the plate is at a depth of 2 feet below the surface of the water. All right, so we have to establish where we're going to put our origin of our x and y axis, and I'm going to go ahead and put it at the center of the circle. So the center, I'm going to try my best at least to put it at the center of the circle. Okay. Move that over here. Okay, so that is my origin. And let's get started with setting up this integral. So we're going to have that the force is equal to the integral from, okay, so where does this circular plate exist in terms of y values? Well, here, because I put the origin at the center of the circle, this is going to exist from y values of -2 to y equals +2. So the diameter is 4, so that means the radius is 2. I'm going up 2 and down 2. So my limits of integration are actually going to be y equals -2 to y equals +2. We're talking about water again, so we're looking at 62.5 is the weight density. And now we need to multiply by the strip depth. So the strip depth, what we need to know is where's the surface of the water, at what y value, based on where we put our origin, is the surface of the water. So we have that the radius was 2, and then the top of the circle is shown as 2 feet below the surface of the water. So that's a height of that water at y equals 4 up there. So y equals 4 is the surface of the water. So finding the strip depth is really just taking the surface of the water minus some generic y value. So it's like, let's pick some y value here and focus on the strip right at that depth of y. So let's say that this is like y equals -1 down here. I kind of missed a little bit, but let's say this is y is -1. So does the equation 4 minus y work? So if I say this y value is -1 right here, how deep is that strip? Well, we could see that it's 4 units plus an extra unit. If this is -1, that's a total of 5 units below the surface of the water. So does this function of y yield +5? Yes, if you plug a -1, 4 minus -1 would tell you that you're at a depth of 5. So the strip depth is found by taking the height of the water minus y. So 4 minus y. And then we need the strip length. So now I need to know how wide this is here. So L of y. So I'm going to need the right side of the circle minus the left side of the circle. And that's why it's key to help us out to put the center of the circle at the origin, because the equation of a circle centered at the origin is easier to find. So I'm going to go ahead and kind of do some scratch work down here underneath the diagram. So the equation of a circle in general centered at the origin is x squared plus y squared equals the radius squared. So in this case the radius is 2, so 2 squared is 4. I'm interested in the right and the left side of the circle, so that means I want them to be functions of y, right? L of y. So I'm going to solve this equation for x. So x squared is 4 minus y squared, or x is equal to plus or minus the square root of 4 minus y squared. So the right side of this circle, the right side of this circle is the equation x equals positive radical 4 minus y squared, and the left side of this circle is x equals negative radical 4 minus y squared. So we can write the function L of y as the right side of the circle minus the left side of the circle. So that's radical 4 minus y squared minus negative radical 4 minus y squared. So minus minus becomes a plus, or minus negative becomes a plus. That's 2 copies of radical 4 minus y squared. And again, that makes sense. So the right side is 4 minus y squared, and we are doubling that because of symmetry. So 2 times radical 4 minus y squared is L of y. So let's plug that in here. 2 times radical 4 minus y squared dy. And so that's our setup, but we are actually going to find the hydrostatic force this time, because this integral is worth practicing. The other ones were fairly straightforward antiderivatives, but this is interesting. So let's take the coefficients, 2 and 62.5, pull those out. So that's going to be 125 in the front, the integral from negative 2 to 2, and then I have 4 minus y in parentheses times radical 4 minus y squared dy. So what I'm going to do here is I'm actually going to distribute here. So I'm going to distribute, and I'm going to have 125, the integral from negative 2 to 2 of 4 times radical 4 minus y squared, extra 4 there, 4 minus y squared, minus y, radical 4 minus y squared dy. And then, because they're subtracted, I can calculate each definite integral separately. So let's make some space here. I'm going to go ahead and, let's see, this integral, I'm going to pull the 4 out. So 4 times that 125 is 500. So I'm going to have 500, the integral from negative 2 to 2 of radical 4 minus y squared dy, minus this, I'm going to do a whole separate integral. The 125 does distribute over here, so I'm going to put minus 125, the integral from negative 2 to 2 of y radical 4 minus y squared dy. Okay, so now looking at these two integrals, let's take a look at this first one. So the square root of 4 minus y squared actually represents a semicircle. So in order to calculate this definite integral, it's really a matter of recognizing, like, oh, this is a semicircle, so a semicircle of radius 2, and we're integrating from negative 2 to 2. So again, this right here represents a semicircle, which, I mean, should be familiar because that's how we, literally found that equation a few minutes ago. So the area of half of a circle, because a definite integral is area, right? The area of half of a circle is 1/2 pi r squared. So I'm going to keep the 500 in front over here. and then it's going to be 1/2 pi, the radius is 2, 1/2 2 squared. So I'm actually solving this definite integral using the area interpretation of a definite integral instead of using general antiderivative or integration techniques. And what technique would we have to apply, by the way, if we didn't recognize this was a semicircle? A trigonometric substitution. So we really want to recognize that we are just integrating, the right side of a circle, and that's half of a circle, and the area of half a circle is 1/2 pi r squared. Now this second integral is a u substitution. So because we have this extra y in the front, letting u be 4 minus y squared will work out nicely with doing a u substitution. So I'm going to show that work over here. Let's let u equal 4 minus y squared. Du is negative 2y dy. I only have a y dy, so I'll have negative 1/2 du is y dy. So my second integral so far, I have negative 125 times an extra negative 1/2 in the front. The integral of, we're going to have radical u, or u to the 1/2 du. But we should be careful here because the limits of integration, we don't want to put negative 2 to 2. Those are y values. We want to change these into u values. So over here, let's do what's u of negative 2? 4 minus negative 2 squared. So that's 4 minus 4, that's 0. And u of positive 2, that's 4 minus 2 squared, that's 0 also. So look at that. If we integrate from 0 to 0, that's 0. There's no area, right, trapped between 0 and 0. So all of this whole side right here is just gone. This is 0, right? So this integral is equal to 0. So all of this is zeroed out. So what do I have left over here? So I have 2 squared is 4 times 1/2 is 2. 2 pi times 500. We end up with this overall answer of 1,000 pi. And the units to our integral is going to be in pounds. In this example, our vertical plate is submerged in water as shown. Find the exact hydrostatic force against one side of the plate. So our plate this time is a trapezoid, and the longer base of 6 meters is across the top and 4 meters is across the bottom. And the trapezoid isn't even fully submerged in water. Only 2 meters worth is submerged in water. 1 meter is above the water. All right, so to start to calculate the hydrostatic force, we need to establish where is the origin of our xy plane. And I'm going to go ahead and put the origin using symmetry at the very bottom of the plate in the middle. Whoops, that's too big. Right in the bottom middle. And so that's going to be my x-axis. And then we're going to have our y-axis up and down through that point. So let's go ahead and start to set up our integral. And so this one, where is our force being applied in terms of y value? So we have y equals 0. But only a portion of this plate is in the water. So only the part in the water is feeling any force. So the part that's submerged extends from y equals 0 only to y equals 2. So far, our force integral is going to look like the integral from y equals 0 to y equals 2. And then we're going to have to put our weight density. But this problem is actually in the metric system of units because we see the distances given or the lengths given are in meters. And so our weight density is going to have to be our mass density of water times gravity. So the mass density of water is going to be 1,000, and then gravity is 9.8. So we have 1,000 times 9.8 is W. So it's the rho times G, mass density of water times gravity. And then we're going to go ahead and need the strip depth. So remember that the strip depth is from the surface of the water to that generic y value that I pick between 0 and 2. So y is, some generic value here, right? So that's the strip there, y. Missed a little bit. so the depth y is at is going to be from the surface of the water to y. So 2 minus y is going to be my strip depth on this one. And we're going to have to put in a little bit of effort this time, more so than the last linear example we had, to find the length of that strip, right? So the length of that strip is this distance right here. This is L of y. So I'm going to have to find, right minus left. So I need the equation of this right side of the trapezoid, which is a linear function. So in order to find the equation of this line, we're going to actually use a little bit of a different process than last time, because this time I don't have the y-intercept. So the other example that we had the y-intercept was 0, 0. So we could jump straight to y equals mx plus b, because b is the y-intercept. But on this one, I don't have a y-intercept, but I do have 2 points. So I can find these 2 points on this line. So this coordinate point right here is going to be the point 2, 0. Since this whole base is 4, half of that is 2. And then this coordinate point here, right, I'm going to be going, this distance is 3 units up. So we could see 2 meters and 1 meter. So 3 meters up, and then over 3 as well. So this whole distance on the top across is 6. So half that distance is 3. So this coordinate point over here is 3, 3. Okay, so how does that help us? So if we have 2 points, we can find the slope between those 2 points, either using the slope formula. So we could either use I'll write it up here off to the side. M is equal to y2 minus y1 over x2 minus x1, because we have 2 points like x1, y1, x2, y2. Or the easier thing to do is just to figure out the slope by finding rise over run between these 2 points. So I'm going up 3 units, and then, so up 3, and then right 1 unit. So that makes the slope of this line, m, equal to 3. So I have slope m, but again, I don't have a y-intercept. But I do have 2 points on the line. So what I can use is point-slope form of a line to find the equation of the line. So I can use y minus y1. So y minus y1, I'll use this coordinate point here, 2, 0. So y minus y1 equals slope m, which is 3, x minus x1. So I'm choosing to use 2, 0 as like my x1, y1. And so I'm plugging it into point slope form of a line. And then I'm going to go ahead and let's see, distribute here, let's say. So this is y equals 3x minus 6. So that's the equation of the right side of this trapezoid, right? So the right side of this trapezoid is y equals 3x minus 6. Well, here's something that's kind of nice. Because of the symmetry here, this is going to have the same y-intercept. So imagine how this line is like going to keep going down. So we just figured out that the y-intercept, now that it's an mx plus b form, the y-intercept is -6 down here. So that means on the other side, like the y-intercept is still going to be -6, but it's going to have a slope of -3 because of the symmetry. So this line on this side is going to be y equals -3x minus 6. So it's still going to pass through -6 way down here, but the slope is going to be -3. Okay, whoops. So let's see here. Now I need to do right minus left, but I need a function of y, L of y. So I need to rewrite these equations as functions of y. So I'll add the 6 to the other side. Let's make some space here. So we have y plus 6 is equal to 3x, and then we'll divide by 3. So we have y plus 6 over 3 is equal to x, and then same thing on this one. I have y was -3x minus 6. If I add the 6 and then divide by -3, I have that right equation. So y plus 6 over -3 is equal to x. So how do I find L of y L of y, that distance, right, is the right function minus the left function. So the right function was y plus 6 over 3 minus the left function, y plus 6 over negative 3. Notice what happens. Minus minus right here and here is going to become a plus. So that's 2 copies of y plus 6 over 3. And again, because of symmetry, that makes sense. Like this right side distance here is just right minus 0. So y plus 6 over 3, this little distance here. And then we're doubling it, right? So 2 copies of that right-hand side, 2 copies of y plus 6 over 3. So that's our function L of y. We're going to go ahead and substitute that in right here into our fluid force integral. So I'll write this as 2/3 y plus 6 dy. And then we're going to go ahead and integrate it. So let's see, we'll multiply all the coefficients. 9.8 times 1,000, and then 2/3, all that can come to the front. So that's like 9,800 times 2/3. We'll bring that to the front. 0 to 2, and then we have 2 minus y times y plus 6 dy. And to integrate this is just a polynomial. We'll have to multiply it out. So we're going to end up with 9,800 times 2/3, the integral from 0 to 2 of, ultimately, we're going to have here like a negative y squared minus 4y plus 12 dy. We can do that term by term integration. So negative y cubed over 3 minus 2y squared plus 12y from 0 to 2. All of that's multiplied by 9,800 times 2/3. So if we plug in the 2 and then plug in the 0, which doesn't do anything, and we multiply it all together, we end up with approximately, this is not an exact answer, so approximately 87,111. So now let's talk units here. The overall units when we are in the metric system is going to end up being newtons. So the force unit in the metric system is newtons, but in the imperial system it's pounds. And if we went back and sort of attached all of the different units back to that original problem, we would see, you know, the units for that 1,000 are in kilograms per meters cubed. Gravity is in meters per second squared. 2 minus y, that's a depth in meters. And then the length is also in meters. So if we look at what's going to happen, meters, 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 and meters cubed will cancel. So we're integrating kilograms per second squared over meters. So y equals 0 to y equals 2 are meters. So when we integrate, we're multiplying the units of the integrand and the units of the limit of integration. So we're multiplying kilograms per second squared times meters, which is equivalent to what a newton is. So we do end up with the unit of newtons here.